All right, we're asked a question here about non-standard electrodes, and they don't come up all the time, but I just want to go through at least one example so you can see how you work with a non-standard electrode. And a standard electrode is a metal, so it's aluminum or zinc or copper or lead, something that you can just take a sample of, put it in your solution, and go. Whenever we have something different, though, that's undergoing a redox reaction like a liquid, it's going to make our cell look a little bit different. So bear with me as we start to figure out how we're gonna make this work. The first thing I'm going to actually determine, though, we've got aluminum nitrate here, so AlNO3,3. Again, the nitrates are spectators, so we basically have an aluminum to aluminum 3 plus going on. And liquid bromine is Br2. It's a Bringelhoff, Br2, and it's going to turn into bromide ions is what we're going to be making out of this. So let's talk a little bit about, first of all, about which one is getting oxidized and which one's going to be reduced. So what I do again is I look at a cell potential chart and I look to see what the values are for reduction potentials of aluminum and bromine. And when I looked at a chart like this, I found that the cell potential of bromine is 1.07 volts and the cell potential of aluminum is negative 1.66 volts. So I already know by looking through that cell potential chart that this is going to undergo reduction and that this is going to be oxidized. And so that's going to help me write my reactions for each of these. Now that I know what's being oxidized and reduced, and again, this is going to be our anode and our cathode, let's go ahead and start by drawing this actual cell. So I'm going to start with just a normal container that is going to have just my regular old aluminum electrode here. And it is going to be in a solution of 1 molar aluminum nitrate. Now, just a reminder, anytime we're dealing with cells, we're generally speaking going to have a 1 molar solution. That's just standard, and that's how our standard reduction potentials are given as well. Now, over on the other side, this is what's really interesting here. I just have bromine, and bromine is going to be my liquid. And so throughout this container, I'm going to have this liquid with my bromine floating around. And I might just put a little L by those so we can clarify what that is. And you might be wondering, how do we make a connection from our aluminum, which is our oxidation, there's our anode over here, that's where our oxidation is occurring, to our cathode? How is it possible for us to make any kind of connection between the two? And what we normally are going to do in this case is we're going to present with some sort of a wire that is not going to be very reactive. And the most common wire to use is platinum. And so we would normally see some sort of a hookup between our aluminum electrode, and I've got a platinum wire, so PT wire, that is going to connect our aluminum to our bromine. And there's our bromine liquid. Again, I'm just going to label this one more time. There's our platinum wire. All right, so the platinum wire really isn't there to partake in the reaction itself. It allows for the flow of electrons, and it allows for things to happen on its surface. So let's talk a little bit about what's happening on its surface. Our aluminum is undergoing oxidation. So again, think about Leo goes grr, or alternatively oil rig. So oxidation is the loss of electrons. So it's going to become more positive. So we have aluminum turning into aluminum 3 plus over here. And we have reduction happening here. So we have Br2 turning into Br minus. Now I know I don't have all of my electrons here. I haven't combined the reactions to figure out my value of N, the number of electrons transfer, but that's essentially what's happening at each. So what's going to be happening here is I'm going to be turning bromine into bromide ions over here. And you might be thinking, well, where is the actual electrode here? The electrode really is the surface of this wire. That's where the electrode is. So it's on the surface of that wire. That's where that reaction is taking place. And really what's happening here is our bromine is turning into our bromide on the surface of that electrode. Over here, it's more standard. We have the aluminum metal, which is placed in the solution, being transformed into more aluminum 3 plus ions. So we're having the production of more aluminum 3 plus ions over here. And over here again, we have bromine turning into bromide. So instead of just having the Br2 liquid, all of a sudden as this reaction continues, we're going to have some bromide ions forming. Now, let's talk a little bit about what's going to happen with that salt bridge. Again, we still need a salt bridge, so I'm going to go ahead and very poorly draw my salt bridge here. And again, the whole point of the salt bridge is to neutralize the solutions where our reactions are taking place. Let's talk about which way our parts of our salt bridge are going to flow. We have K plus ions and NO3 minus ions in our salt bridge. So again, on the oxidation side, I have the formation of more aluminum plus 3 ions. And so in order to neutralize that, I need more negatively charged ions. So I'm going to have the nitrate ions from my salt bridge flowing into solution over here. Alternatively, if I look over here at the bromide side, I'm forming more negatively charged bromide ions, so I'm going to need the potassium ions to flow from the salt bridge into that solution. So again, the whole point of a salt bridge is to keep the electrical neutrality in the system and on each side. And so we're going to have those ions flow into solution in order to make them more electrically neutral. Where are the electrons going to flow? Let's talk about that next. So let's talk about where the electrons are in this reaction. My electrons are over here for this reaction, and over here my electrons are right here. Again, this isn't balanced, so that'd be 2 and a 2. And we all know that in order to make their final reaction, we'd have to multiply each of these. This one by 3 and this one by 2. Regardless, though, we have the aluminum producing electrons, the bromine using electrons. And so like always, our electrical current is going to flow from the anode to the cathode, from where the electrons are being produced at the anode, that's where they're being made, to where they're used at the cathode. And so if I were to draw electron flow on this platinum wire, it's going to flow left to right. Now let's say I put a voltmeter on there and wanted to know how much voltage, what would it read? I go back to the numbers I used to figure out what my anode and cathode are. So we said that our bromine was our reduction, so it's 1.07 volts. I keep that the same sign. Our aluminum was negative 1.66 volts for reduction, so I have to just flip that sign. And when I add those two together, I should see a voltage reading of 2.73 volts. So that is, in essence, how a non-standard electrode works. Again, we just have a platinum wire, something that's non-reactive, in order to complete that circuit. And the electrode really is occurring on the surface of that wire. Notice I'm only drawing a circle around it when it's inside that liquid solution, because that's really where that reaction is taking place.